Okay, well, welcome back, everybody. Just a couple of quick announcements. Number one, I'm looking at the schedule, and we have roughly about 8 more meetings, Zoom meetings here, which I believe it also includes the last one, which is a Tuesday, which is the final, which normally we don't have a meeting, but I'm here on Zoom in case there's any questions for the final. So given that we got chapter 14, chapter 15, we are about halfway done with chapter 14. Chapter 15 is extremely small. So what I'm going to do is for the remainder of the meeting, starting next week, we will make Tuesday a lecture day, which I would do a Zoom, and we'll continue with the chapters until we're done with them. Okay. And then we'll make Thursdays a self-study day. Yes, I will be here. I won't have office hours. So what I'm going to do in lieu of office hours, you can come to your regular section here during this time period with any questions. Now, you're more than welcome to come. I'm going to do it for both my sections. So you're more than welcome to come not only to your 4:15, but to my 1 o'clock. And so that'll prepare you for the final. The final, FYI, is a comprehensive exam. It encompasses all chapters. So, just want you to be ready for that. And let's see what else. A reminder that any missing assignments with respect to activities and homework, those can be done until the last day. Okay, but as you know, they do have a due date. Questions in the final, I want to say previous exams, roughly 60. Let me double check that. It is 60, all of them multiple choice, roughly 2 to 3 maybe per chapter ballpark. There is a practice final exam on the course website, so you might access that. I've also included that in your module, so to give you an idea of what type of questions asked. Timed, yes, it's 110 minutes, so you basically almost 2 hours. Okay, so, and it will be opened up, and so you gotta, giving you a heads up, we're like, 4 weeks away. So adjust your schedule accordingly and make sure you can give yourself plenty of time. Okay. Now, I since Tuesday is the last day, if that final exam day doesn't work for you, I can move it forward 1 or 2 days, depending on your work schedule. A lot of you have work schedules you got to work around, or other things. I can do that, but I can't move it after Tuesday. So, keep that in mind. Prepare yourself for that time. Now, prior to that, we also had the last regular exam number 5. So keep that in mind too. So get yourself, organized time-wise and time management and all that. Okay. All right. Any other questions? All right, well, given that tomorrow is Veterans Day, I just want to thank, I have a few veterans in my class out there, so I'm hoping that you can balance that equation, right? Okay, hydrogen in the presence of oxygen reacts to keep the water. So anyway, thought I'd put that up for you. We were on chapter 14. Obviously, and we were talking about IMF. These are intermolecular forces, okay, as compared to intra. Now, inter deals with the interactions of molecules with each other or other molecules of something else, but those are interactions that are occurring out there. whereas intra deals with the type of bond that is occurring. And so we have to distinguish the two, okay? And I think, let's go back here. We distinguish the two types of forces. One is a bond, which is the ionic bond, which consists of a metal and a non-metal, okay? Now, someone brought up the question, which is a very good question, and asked, well, wait a minute here. I always talk about electrons on the outside surface, and they have negative charge, and you know, why is it that we have an ionic bond that you got positive charge and a negative charge? And that's a valid question. And so I want to remind you about ionic bonds, that we look at the elements, and remember the metals lose electrons. So if we take, for example, to refresh your memory, let's take example sodium. Sodium, atomic number 11, has 11 protons and 11 electrons. We got 11 positives and 11 negatives. Furthermore, it's a metal and it's going to lose electrons. All metals lose electrons, okay? Next point is in group 1, meaning that there's one valence electrons, 1A, it's in group 1A, so it has one valence electron. So it would lose that one electron to obtain the next level in, which would be full of electrons, and obtain that octet. The driving force is that octet, okay? So sodium now still has 11 protons, but instead of 11 electrons, it now has 10. Okay, so the 10 positive protons counter the 10 negative electrons, but you still has one more positive proton. So it has a net positive charge, even though there are electrons on the outermost shell. The fact that it has a net positive charge is because it lost an electron. On the other end of the spectrum, the nonmetals gain electrons, and the driving force of them also is to get the octet. And so by gaining an electron, 3, 2, or 1 electrons, they fill the outermost shell, and now they have an excess number of electrons compared to where they started as an element. So fluorine has a total of 9 protons and 9 electrons. When it becomes an ion, specifically an anion, now it has 10 electrons. And so the 9 positives and the 9 negatives cancel each other out, but there is one excess net negative charge, and hence it now has a negative charge. So now you have an ionic interaction between the positive ion, cation, and the negative anion, which come together and form an interaction and attraction, specifically an ionic bond. And they're not bonded together, they're electrostatically attracted to each other because of their distinct opposite charge. Just like two magnets coming together, they're just attracted to each other. Now, with respect to covalent bonds, that's because two nonmetals come together. I repeat, that's because two nonmetals come together and they literally form an actual bond. They share electrons to form a bond, be it a single bond, a double bond, or a triple bond. Now, when that sharing is equal, okay, that is because the two elements they came together are the same, like all diatomics, or they are carbon and hydrogen. Their electronegativity being the same are both equal. Therefore, there is no pull of electrons. The electronegativity is a measure of the affinity of an atom has for electrons onto itself. The affinity for an element to want to pull electrons onto itself. So the stronger, the greater the electronegativity, the greater the pull, resulting in a dipole, a permanent dipole in a covalent bond, which we call a polar covalent bond. And that results of the coming together of two dissimilar atoms. There's a question here. Oh, oh, thank you, Megan. Uh, the scenario that I utilize is the A scenario, meaning that the two elements that are bonded together, be it a single, double, or triple bond, are the same. And therefore the electronegativity is the same. Therefore, the pull of electrons is equal. The AB scenario is a situation where I have a totally two different elements forming a covalent bond, being a single bond, being a double bond, or triple bond. It makes no difference. The fact is there are two dissimilar atoms, non-metals, and there is going to be a pull because one of these guys is going to have a stronger pull of those electrons, and we end up with a permanent dipole. Okay. And so, for example, if B has a higher electronegativity, then the electrons are pulled away from A toward B, not pulled away totally, just partially, resulting in a partial positive area, meaning that the electrons that were distributed around A have been pulled away, resulting in a more positive character, okay? And the negative side, the partial negative side, the electronegativity is stronger, so it's pulling the electron density toward B in this example, and therefore overall has a lot more negativity, a lot more negative character, and therefore has a partial negative charge, okay? All right, now with respect to the AA scenario, don't forget that the CH bond always nonpolar. And you might think, well, we got two dissimilar atoms there. Yes, however, their electronegativity is such that they're almost the same, that and for all intents and purposes, it's a nonpolar bond, okay? Those are the bonds, those are the intramolecular interactions or forces involved. That's within the molecule. When we start dealing with interactions with other molecules, be it the same molecule or even different molecules, then we talk about intermolecular forces, okay? And there are three of them that deal with covalent compounds. These are all covalent, okay? The last one deals with ionic compounds in the presence of, most of the time, 99% of the time, in water. It's an aqueous solution, all right? And so for the covalent compounds, when the species, when the molecule is nonpolar, the only force it has is the London forces, okay? Those are the interactions that are occurring with other molecules that are nonpolar. When there is a dipole, as a case of a polar covalent bond, then we're dealing with a polar molecule, okay? So they have a permanent dipole. Now, hydrogen bridging, yes, it is a dipole, but it's a very special type of dipole. It has an additional property in that it is only for those atoms, specifically nitrogen, oxygen, and fluorine, that are bonded to hydrogen, okay? And with respect to a little more, being a lot more strength, it is. Hydrogen bridging forces are a lot stronger than the dipole-dipole, though even though hydrogen bridging is a dipole, okay, it is a dipole, but it's a special kind of dipole that because of its specialty, it has its own name, and it's called hydrogen bridging force. But only, I repeat, only for those hydrogens that are bonded to nitrogen, oxygen, and fluorine, okay? And then the ion dipole forces, normally, like I said, we gotta have normally a salt, which is an ionic compound, and most of the time being ionic, they are in an aqueous solution, okay? All right, sorry, excuse me, I got Something making me sneeze here. All right, so those are the forces that we're dealing with. Now, given that information, what we're going to be able to do is to do a compare and contrast, a relative compare and contrast with molecules. And so we need to first define what type of molecule we're dealing with. Once we define it, we can assign to it what force it has. And once we have that information, we can look at 2 or 3 different molecules with their forces and determine, okay, who would have a higher boiling point? We can look at some physical properties, okay? Because the thing to remember is this: when it comes to intermolecular forces, what we're going to be dealing with is how strong these interactions are with molecules with each other. So I got a molecule here, and they're interacting. They're not forming a bond, they're forming an attraction to each other due to the type of force that they have, okay? And so when we put energy into the system, we're trying to break that energy, that system, of that interaction apart. When we boil water, the energy is going into the system to break that interaction of the water molecules that are in the liquid stage. And we continue to put energy into the system so we totally break that interaction apart and then cause that liquid water molecules to go into the air as vapor, okay? So the stronger that force is, the more energy it requires. So telling you that the London forces are the weakest of the 3 should tell you that any nonpolar species would have in general lower boiling point compared to, say, a hydrogen bridging force molecule that has stronger forces, and their boiling point will be higher, greater, because it requires more energy to break up that interaction, okay? And those are the type of relative things we're going to compare and contrast, but we have to grasp the forces and be able to assign forces to the different molecules so we can come to a conclusion with respect to the molecules that we're going to look at. All right. So now you have a table here where we have the elements in the first column, the molecule, and then we have to determine, is it polar or non-polar? Well, to answer that question, you have to go back to the Lewis dot structures. You may have to do that, okay? Because the Lewis dot structures then tells us the geometry of that molecule. And then once we learn about the geometry, and then we learn about the type of bond, whether it's a polar bond or a non-polar bond, then it tells us what the whole molecule has, whether it is polar or non-polar, okay? Once we know that, we can assign to it a intermolecular force. All right, so we had done carbon dioxide before, and we did the Lewis dot structures, and if you recall, let me change the color here. We came with this structure, okay? This Lewis dot structure, okay? Now, once we did that, we identified the polar bonds. Now, we have the carbon-oxygen bond, if you recall, which is a polar bond, okay? It is two dissimilar atoms. It is that scenario of A and B, okay? So we have a polar bond. Now, I drew the arrow from carbon to oxygen because I know that with respect to carbon and oxygen on the periodic table, oxygen is closer to fluorine. Fluorine is the most electronegative element there is, okay? So to determine who's more electronegative is we look at the their position in their periodic table. So that tells me that oxygen is a lot more electronegative than carbon. I don't have to memorize its absolute value. I just have to know its position relative to fluorine. So that being the case, oxygen being a lot more electronegative, it is pulling the electron density onto itself. So I draw the arrow from left to right, and I do the same on the other direction, okay? So now, based on the Lewis dot structure, then we identified the bonds. Now we look at the dipole bonds and we determine that they are going in opposite direction of each other, okay? Opposite direction. Those arrows are going to the left and to the right, which means that they cancel each other out, which means that polar bonds that cancel each other out in the molecule due to their geometry results in the whole molecule to be non-polar. Okay, so carbon dioxide, though it has two polar bonds, it is non-polar. Other geometries that exhibit that behavior are tetrahedral. To refresh your memory, if we had, let's say, carbon tetrachloride, it would have this structure right here, tetrahedral. It has 4 polar bonds, okay? 4 polar bonds. And at first sight, you would think, okay, 4 polar bonds would suggest a polar molecule. But because of the geometry, all 4 polar bonds cancel each other out, resulting in this case, also a non-polar molecule, okay? Once we determine that the molecule is non-polar, we can automatically assign to it an electromagnetic, an intermolecular force, which is London. That is the only force that any non-polar molecule would have, just London forces, okay? Next example, PF3. Well, you may not know what that is. You can look it up and everything, but my suggestion is you go back and you do the Lewis dot structure. When you do that, you will come up with the following structure. Okay, which then also ends up with a pair of lone electrons on the central atom. The general formula would be AB3E. Lone pair on the central atom. Automatically, without even having to do anything else, the fact that you got a lone pair in the central atom is going to tell you is that you have a polar molecule, okay? Anytime you have lone pair on the central atom, I repeat that, on the central atom, not on the other atoms that are bonded to, but on the central atom, you will have a polar molecule, okay? This is very similar, if you think about it, to ammonia, which I asked you to memorize because we're gonna see this guy lots. Here's ammonia. Guess what? It's got a lone pair on the central atom. Very polar molecule. Another example is water. We also did the Lewis dot structure in water, where we ended up with 2 lone pair on the central atom. An extremely polar molecule, okay? Water is the most polar molecule there is. Now, once we determine its polarity, let me clear up my mess here. Now we have to assign the electromagnetic force. Well, point number 1, we can eliminate the London forces, okay? Why? Because it's polar, okay? We can eliminate the ion dipole interaction. Why? Because there's no mention here of ions, it's PF3. Okay, we eliminate that. So what we have left over is the dipole-dipole and the hydrogen bridging force. Okay, now the question is, well, which one? Well, let's break it down. Hydrogen bridging force, what is required? Hydrogen. Okay, we don't have hydrogen here. It's just phosphorus and fluorine, so we can eliminate that. So the obvious, by process of elimination, we determine that the force it has for PF3 is the dipole-dipole force. Okay? All right. Next one, we have HF. That's a good hint right here. You got hydrogen. All right. And so First of all, we have to determine, is this polar or nonpolar? Well, this is a scenario of an AB, okay, scenario. Automatically, we have apolar species. Okay. Now we have to determine, we can eliminate London forces and we can eliminate ion dipole, right? Because no ion involved here. So now we have dipole or hydrogen bridging forces. Well, the fact that we see hydrogen, the fact that you have fluoride involved should help you deduce what force you're dealing with, and that is the hydrogen bridging force, okay? Because again, hydrogen bridging force is only for those examples of hydrogen bonded to nitrogen, to oxygen, or to fluoride, okay? Hydrogen bridging force. All right, now we have the carbon, hydrogen, hydrocarbon. That's all you see there, carbon, hydrogen. That in itself, the fact that you have a hydrocarbon automatically should tell you, I have a nonpolar species, okay? All hydrocarbons are nonpolar, all of them, because the carbon-hydrogen bond, first of all, hydrocarbons consist of nothing but carbon-hydrogen bond, and the polarity of the carbon-hydrogen bond is nonpolar because they have very similar electronegativity. So all hydrocarbons are nonpolar regardless of how big they are. Now, this is one carbon, but you can have, polystyrene. Polystyrene, for example, is made up of nothing but carbon and hydrogen. It's a hydrocarbon. All right, and it is nonpolar. Okay, because you know that because you use polystyrene cups to drink water, right? Liquids. But if I put that polystyrene in a nonpolar solvent, guess what? It dissolves like crazy. All right, so being that methane is nonpolar, automatically we have a London dispersion forces for that chemical. And that will be true for any hydrocarbon. All right, then finally at the end, we have Ki, which is an ionic compound, and then it's an aqueous system. The fact that you're dealing with ionic compound tells you I got an ionic compound in polar water, and the only force involved here has to do with ion dipole. Okay, and so when we look at these, the ones I've done here, these are all covalent compounds. Okay, the last one deals with ionic compounds. And all ionic compounds, the only force involved there is ion dipole. That's it. Okay. And covalent compounds, depending on the polarity, can be London dipole, and if it's hydrogen involved, then we're dealing with hydrogen bridging force. Now, with this information, now we can do some relative comparison, let's say with some physical properties, which we're going to do down the road here, but let's just talk about boiling point. That is the temperature that a liquid will convert from liquid to vapor phase. That is the boiling point. Water boils at 100 degrees Celsius, 212 Fahrenheit, but we deal with centigrades, okay? 100 degrees Celsius. All right, so now we can't give it absolute values, but we can do a relative comparison once we assign which IMF is involved with the molecule. So what we can deduce is the following. With respect to boiling point, the one with the hydrogen bridging, we would anticipate, we would predict that to have HF to have the highest boiling point relative to the other molecules that we're looking at, okay? Because its intermolecular force is the hydrogen bridging force, and that is the strongest force. So in order for HF to boil, it will boil at a higher temperature because it requires more energy more energy to break the interaction up. All right. The group that will have the lowest boiling point will be the ones that have London forces. So these would have the lowest. I can't tell you specifically the absolute value, but I can tell you relative to the other two, it would have the lowest boiling point. In fact, we know that carbon dioxide at ambient temperature is a gas, so is methane. Okay, their boiling point is way negative. We're way down there in the scale. So it's very, very, very low. Okay, and then the PF3 will be somewhere in the mid-range between the HF and the gases. Okay, so that is what we mean by relative comparison. And boiling point is just one physical aspect. We can look at also and do a comparison with surface tension, even melting point if they were liquid, solids, and look at what I say, surface tension, and look at vapor pressure. We can look at relative physical properties of these molecules and do a compare and contrast. But I overemphasize we can't give absolute values, we can only do relative values, okay? But in order to do that, anything to do what we just did, we have to be able to assign it, the molecule, we have to assign it a polarity, okay? And then analyze, once we know it's polar, nonpolar, we can assign the force. Now, the difference between assigning a dipole-dipole versus a hydrogen bridging, straightforward. Only when you got hydrogen interacting with bonded to nitrogen, oxygen, fluoride. If that's not the case, then it's simply dipole-dipole. Okay. All right, well, what we have here is something called Coulomb's law. And we're not gonna do a lot of emphasis on this, okay? But I'm just gonna give you some general information about Coulomb's law. But you know, you are probably already aware of it, you probably didn't know about it, okay? Just, it's a lot. Now, let me give you an example. I'm sure some of you have maybe played with magnets, and you've taken two magnets and maybe put the opposites in each other and then bring them together, like two norths interacting. Well, they're gonna repel each other, right? Now, if I got the two magnets and they're like this far away, yeah, you're not gonna feel much repulsion between the magnets, right? Because the distance is quite a distance away. Now, as I bring those two magnets together, and depending on the strength of the magnets, you can start feeling that repulsion occurring. And as I get them even closer together, you can probably feel that force even stronger as far as being repelled, okay? And that's what Coulomb's law is kind of dealing with. We're talking about the interaction of charges with each other, okay? And what Coulomb's law states is that the force of attraction between two charges is directly proportional to the magnitude. Well, that makes sense. If I got a charge, two charges of the +1, okay, and one charge is increased to say a +5, so obviously my force between a +1 and +5 increases. That stands to reason. But then it further goes on to say that it is inversely proportional to the distance between the two charges squared. Now, what does that mean? Well, let me show you the equation here. All right, we're not, you know, we're not going to ask you to memorize the equation, but understand what's happening with this equation. Well, let's take that equation. What I'm going to do is I'm going to take K, Q1 and Q2, and I'm going to combine them to make a one variable, because K is a constant and Q we're going to keep constant at, let's say, a unit of 1. Okay, so I can do that and just keep everybody constant and redefine that as F is equal to, let's call it X over R squared. Okay, R squared is the distance between these two charges. Okay, so let's take an example, and let's say in the first scenario that we make R equal to 1. Now the unit here, we could say centimeters, we keep it 1 centimeter, okay, just for argument's sake. Well, we plug in R equal to 1 in that equation, and simply F, the force, is simply X, whatever X may be, okay? All right, so let's double R. So we're going to go from 1 to 2 units, okay? So now F is equal to the force divided by 2 squared, okay? Which is equal to X divided by 4. So what we have in effect, we have reduced the X value by 25%, a quarter. Okay. When R equals 1, X is simply, the force is simply X. When we double that distance, we reduce that force by 25%, 0.25. Okay, the force, and that's an effect. You take those two magnets, and you've seen this, right? Spread them apart. That force gets smaller. You don't really feel that force because the distance is greater. Now let's go the opposite direction. Let's reduce the third scenario where R goes to 0.5, half of where we started. And so now we have F is equal to X divided by 0.5 squared, okay? Which is equal to X divided by 0.25, which is equal to 4X, okay? And so that scenario where it's inversely proportional to the square greatly magnifies the interaction, the force between two charges when you reduce the distance between them by half. In fact, by reducing the distance by half, you have increased its force by a factor of 4. Doubling the distance away by doubling it decreases the force by a quarter. So that distance is very crucial as far as the interaction between forces and molecules with each other, okay, depending on what they are. So that's a takeaway for this Coulomb's law, just to say that the force of charges repelling or interacting is basically affected by inversely proportional by the square of the distance between them, okay? What I mean by inversely proportional, directly proportional would be the force and Q's. If I double Q or triple Q, the force goes up. That's directly proportional. But when you increase one variable and the other variable drops, that's inversely proportional. And that's what it means normally in the denominator of your equation, okay? And then to magnify it is to the square of that distance. All right, so enough on that, but basically that's what we're talking about. All right, so what we're gonna do here, we're gonna talk about this slide, and we're probably gonna stop it here, okay? So, all right, so here what they're asking you to do is determine, choose the bond or the IMF described for each example below. All right. So basically what they're saying is this. Read the question. From the question, determine if you're dealing with the intermolecular forces or the intramolecular forces. Okay. And that is defined by the wording in the sentence. If we are talking about how these atoms interact with other atoms, then obviously it is the inter. If we're talking about how a bond is held together, how two elements are held together in a molecule, then we're talking about the bond, and then we have to determine what type of bond we're looking at, okay? So look at the first question. It says, what holds the atoms together in one ammonia molecule? Okay, keyword one. And so what do you guys think we are talking about here? Do you think we're talking about inter or intra? What do you think? Okay, we'll read the question again carefully. What holds the atoms together in one ammonia molecule, NH3? Are we talking inter or intra? What do you think? Oh, let's think that over now. Inter, okay, we're talking about one molecule. Remember, inter deals with other molecules. Okay. So we're dealing with one molecule, so that yes, that would be intra. Exactly. So it's asking us, what is holding the atoms together in one molecule of NH3? And so what we're looking at is intra, meaning, okay, what type of bond are we dealing with? Okay, so what type of bond are we dealing with? We have a bond of nitrogen and hydrogen. Obviously, that's a covalent bond, right? Two nonmetals. But then what type of covalent bond? Polar or nonpolar? Nonpolar? What type? Well, wait, there you go, polar. You're right, Samantha. It is a polar bond. This is an example of A-B scenario. I have two dissimilar atoms between nitrogen and oxygen, so automatically I got a polar bond. Okay. All right, so we're dealing with polar covalent bonds, okay? And that's why it's important that we read the question. Not trying to be tricky here. It's just the way the questions is written, and we're trying to figure out. It's the first thing you ask yourself. Inter, intra, which one is the question asking about? Then from there, we can then assign it a type of bond. All right, so next one. What holds, it's polar, yes, because all the three nitrogen-hydrogen bonds are polar, okay? They're polar in themselves. And we have a lone pair on the nitrogen. If you do the Lewis-Dot structure, you'll find for ammonia, you have, you draw that, you end up with nitrogen bonded to hydrogen, three of them. Then we get a lone pair. Now, just looking at the nitrogen-hydrogen bond all by itself, just in itself right there, we have a polar bond. Okay, because we have the scenario of an A-B relationship. Okay, where we have two dissimilar bonds. Now, the fact is this: if this were tetrahedral, then these both polar bonds would cancel each other out. But we have lone pairs sitting up here. And because of that, if you recall, we talked about this, how the lone pairs take up more space. So they squish those other, like an umbrella inverted itself, they squish the nitrogen-hydrogen bonds down, resulting in their polar bonds, those three polar bonds do not cancel out, okay? Resulting in a polar molecule. Okay, and that is correct. No fourth to cancel out because the lone pair squishes them all in. All right, good question. All right, now, what is holding the sodium ions in water? Okay, and so here, first flag, you have an ion, okay? And so you're like, And then second flag, you got sodium ions in water. You got sodium, salt water, basically, in water, in salt in water. Okay. Now it could be sodium chloride, but it could be, it's some type of a salt. So we're not looking at bonds within sodium. We're looking at the interaction of the sodium ion in water. And there's only one example, and that is the ion dipole example. That is the only one. Remember, when they talk about an ionic compound and they mention a polar solvent, then you're dealing with ion dipole interaction. Ion dipole force. Okay. Look at the next one. It says, what is holding three HCl molecules together? Now, the question is this, we go back to the intra or inter. I should have said here, the fact I should have mentioned in the sodium water, the same question, because this is an interrelationship, sodium and water. Now the question so once we know that, being inter, we have four forces to work with, right? Well, sodium is not covalent, so those first three would not function. So the only logical choice you got is the ion. All right, now we have three HCl's. What is holding them together? So we have to answer the question, are we dealing with inter or intra interaction here for this question? Okay, what do you think? The key word, what is holding three HCl molecules together? So we got three molecules sitting out here. Okay. And so what is holding them together? What type of force are we dealing with? Are we dealing with inter or intra forces? Oh. Not intra. Remember, intra is if we are dealing with just one molecule. But whenever we deal with more than one molecule, as the question says here, then we're dealing with inter relationship, okay? So we're dealing with the inter here. Now the question is, well, which one? Well, you got four choices, right? You got London, dipole, hydrogen bridging, and ion dipole. Well, we can eliminate ion dipole because we don't have ionic compound. ion dipole only deals with ionic compounds, specifically, a metal, non-metal combination. So we can eliminate that. Can we eliminate London forces for HCl? Yeah, right, because is HCl polar or non-polar? Is hydrochloric acid polar or non-polar? What do you guys think? Okay, well, what kind of, it's exactly, it's polar, all right? It's an A-B scenario, so automatically we got polar. All right, so being polar, being that we're doing intramolecular forces, we eliminated the ion dipole because we're not dealing with ions, ionic compounds. It is polar, so we can eliminate London dispersion forces, get rid of that, right? So what do we got left? We got left dipole-dipole or hydrogen bridging force. All right, well, let's work on hydrogen bridging force. Hydrogen bridging force is only for hydrogen, which you have, hydrogen, okay? But when it's bonded to nitrogen, oxygen, or fluoride, which that's not the case here. So the only thing left over is dipole-dipole force, okay? You see, let me clear up my mess. And I'll rehash that, okay? First thing we had to identify is we're dealing with 3 HCl molecules. So we are dealing with intermolecular forces, okay? Not the intra, because we're dealing with 3 HCl molecules together. What is holding them together, okay? Once we determine that, remember we have to determine the polarity. We just determined that it is a polar species, okay? Step 1 is determined that it was inter. Step 2 was determine the polarity, which is polar. Why? Because we have that scenario, we got an A-B situation, 2 dissimilar atoms, polar automatically. No more questions you don't need to ask yourself anymore, okay? Once we know it's polar, now we look at the IMF forces. Well, we can eliminate London dispersion forces. Why? Because it is a polar compound, and only nonpolar species have London dispersion forces. We can eliminate ion dipole. Why? Because we're not dealing with any ionic compounds here. Nothing said about like a metal ion, okay? Yes, I understand hydrochloric acid becomes ionic to form protons, but that's not the type of ion compound we're talking about. We're talking about metal ions, so we can eliminate the ion dipole. What is left is dipole forces or hydrogen bridging force, okay, of those 4 forces. Well, let's eliminate HBF, because first we do have hydrogen, like I stated, but HBF is only true for hydrogen bonded to nitrogen, oxygen, or fluoride, which this is not the case, is bonded to chloride. So we can eliminate HBF. So the only choice left is dipole-dipole. And that is my systematic approach to attack these problems, okay? Eventually, as you become more comfortable, you can obviously bypass a lot of these steps, but my suggestion is go through a systematic approach until you reach that stage. Okay, let's clear this up. And so we have, oh, what did I do? HCl dipole forces. I jumped ahead. Now, and what is holding the ions together in salt, and specifically sodium chloride? Well, there's no mention here of water, so we're talking about just salt to salt, solid form. Okay, so is basically what type of bond it is, okay? And it's asking you what is holding the ions together. So that is a intramolecular question, intramolecular force question. All right, now, next one. What is holding 4 H2O molecules together? All right, so inter or intra? What do you think? Okay, let's think about it. Go back up here. We had 3 HCl. Here, this question is saying 4. So are we dealing with inter or intra? We're dealing with inter, okay? Inter is how molecules are interacting with other molecules. Okay? A good analogy is college sports. You have intra-collegiate sports, which are sports you play within your college. Okay, you may have, you know, I don't know, a volleyball team from this department and that department. You're playing within the college. And then you have intercollegiate sports where, you know, GCC is playing with, I don't know, SEC. You know, you're playing with other colleges. Those are intercollegiate sports, okay? So maybe that might help to keep the two prefixes straight. So the question says 4 H2O molecules, so having more than one molecule directs you to inter. So once we determine that, now we determine what's the polarity of H2O. Is it polar or non-polar? Very polar covalent, exactly. Now, once we know that, we can assign one of the 4 forces. The fact, again, that is dipole, we can eliminate the London forces, eliminate those, and we can eliminate the ion dipole. Okay, because there's no ions mentioned here. We're just talking about 4 water molecules. So what is left is the dipole, dt, and the hydrogen bridging force. Okay, dipole force, and hydrogen bridging force. Well, let's look at the formula. Let's look at the structure. The structure of water, if you recall, was as follows. Okay, we have hydrogen bonded to oxygen, and that right there, hydrogen bonded to oxygen, should direct you to HBF, because it directs you there, and then you verify, is it hydrogen bonded to those 3, not on file, as I call them, nitrogen, oxygen, and fluoride? Yes, it's bonded to oxygen. So that means we can eliminate the dipole forces. And for water molecules, the forces involved there are hydrogen bridging force. Okay. All right, now here's another, get this out. What holds nitrogen gas molecules to each other? Okay. Intra. What do you think? Inter versus intra for this question. Okay, what holds nitrogen gas molecules to each other? To each other, that wording, what does that suggest? Inter or intra forces? Inter, exactly. Okay, so we're dealing with inter forces. Now we got to assign polarity. Nitrogen gas is diatomic. Okay, what is the polarity of nitrogen gas? It's covalent, no question about that, but which one? Polar or non-polar? Non-polar, exactly. And since it's non-polar, the only force involved for non-polar species is London dispersion forces. Okay, London forces. See how we went through that? Inter, intra, polarity. Polarity, assign the force. Okay, all right. What is holding the oxygen together in an oxygen gas molecule? All right, so inter versus intra. What do we got here? What is holding the oxygens together in an oxygen gas molecule? Okay. Is it an interforce or intra-force? What do you guys think? They're both molecules, right? Well, it says, what is holding the oxygens together in an oxygen gas molecule, which is O2, okay? So there's only one molecule they're talking about here. And they want to know what is holding these two together. So we're dealing with an intra force, okay? And so we need to know what type of bond. Exactly. What type of bond would that be? Obviously covalent, but more specifically, it would be a non-polar covalent bond. Okay. And then finally, the last one, we're talking about ammonia molecules, and here, keyword, two ammonia molecules together. And so inter, intra, what do you guys think? Exactly. Since we're dealing with two molecules, we're looking at the interaction between them. So we're dealing with an interforce. And now we have to identify which one. Okay, so again, process of elimination, ammonia, polar, non-polar. What do you guys think? This is one of these that you want to put in your long-term memory. Ammonia, extremely polar. That is correct, Samantha. Now, it is polar. All right. Given polar, we will not have no London forces, and we will not have any ion dipole forces. And so the only thing left is it a hydrogen bridging force, or is it a dipole-dipole force? Okay. Which one do you think? Hydrogen bridging force, exactly. Because if you look at it, we got nitrogen bonded to hydrogen. Okay. That sends me to this force right there. All right. So we can eliminate the dipole-dipole. And so hydrogen bridging force would be the force involved in holding two ammonia molecules together. Okay. And if we were to look at, say, relative boiling points, the hydrogen bridging force examples, which will be right here and right here, those guys would have the highest boiling point, okay? Because that they have the strongest boiling, the strongest force involved. the ones with the London forces, like that one, would have the lowest boiling point, which again, nitrogen is a gas in 25 degrees. And one of the reasons it's a gas at this temperature is because their interaction with molecules is not very strong, and it very readily can be separated with minimum amount of energy. Okay. And then the dipole forces like this, they'll have some boiling points somewhere into intermediate. All right, so what I'm going to do, I'm going to stop it here. We'll stop it here at slide 18. And